Okay, transformers. Here's a transformer. You have a primary coil on one side with a certain number of turns and a secondary coil on the other with another number of turns. Okay, first question. There's an alternating current in the primary coil. State what is produced in the iron core. Okay, you just have to remember this. It's an alternating magnetic field or a changing magnetic field. Alternating makes you sound more intelligent, so we'll use that word. There's an alternating current in this coil, which means the current is changing direction all the time. And that's important because that means that the magnetic field in the coil is also changing. And the magnetic field, which, for want of a better phrase, is trapped inside this iron core, because it's changing here, it's also changing inside this coil. And you need a changing magnetic field in order to set up a potential difference in the coil. And that's how transformers work. Anyway, to cut a long story short, just say an alternating magnetic field is set up in the iron core. Okay, right. So we're told that in some coil, the number of turns on the secondary coil is 1. The secondary voltage coming out here is 11.5 volts. And we're told that the primary voltage, that's this one here, is 230 volts. And we have to work out the number of turns on the primary coil. Okay? So, the equation we're going to use is the voltage on the primary coil divided by the voltage on the secondary coil is equal to the number of turns on the primary coil divided by number of turns on the secondary coil. Okay? Remember that equation. A good way of remembering it is that the ratio of the voltages from there to there is the same as the ratio of number of turns. The number of turns directly determines the voltage, if you like. Anyway, right, we want NP, so rearrange to make NP the subject. So bring NS up here. So NP is NS times VP over VS. Always rearrange first and then put the numbers in at the end. Okay, so rearrange, put the numbers in. NS is 1, VP is 230, and VS is 11.5. And that turns out to be 20. Number of turns in the primary coil is 20 turns. Okay, right. Okay, it tells you in this transformer that the power coming out is less than the power going in. Why? Well, no machine is 100% efficient. Okay? You can get very close to 100% efficiency, but in reality it's not really possible. So the answer is that transformers are not 100% efficient. Okay? If you want, you can give them a reason. Energy is probably lost as heat. But just say that most transformers, the power out is less than the power in because most transformers are not 100% efficient. Okay, what's next? Right, this thing here. Right, there's a voltmeter and it's connected to a coil, and these two students are pushing this coil through around a magnet. Okay, student 1 gets these results for the voltage or potential difference, same thing. And student 2 gets these results. 4 different numbers of turns in that coil. Okay, just quickly, to make sure you know why a potential difference is produced, it's the same thing, same principle as this. There's a magnetic field around the magnet, and the coil, when you push it down, it's cutting the magnetic field lines. So there's a changing magnetic field in the coil. And a changing magnetic field in the coil sets up a potential difference in the coil. And that's what they're measuring. Okay, right. State the resolution of the voltmeter and why is this resolution suitable for this experiment. Okay, look at the results that the students are getting. The resolution must be 0.01 volts because that's the smallest difference that this voltmeter can measure. It can measure 0.51 volts and it could measure 0.52 volts, for example, but it couldn't measure 0.513 volts, for example. So it's 0.01 volts. Why is this resolution suitable? Well, it's suitable for this particular experiment because if you look at the number of turns they've chosen, they've stepped it up by 5 each time. And every time you go from one to the next, you get a different reading, a different result. It goes 0.09, 0.20, 0.31. So the reason it's suitable, this resolution, is that each reading you take has a different answer, a different result. And you've got to have that feature in an experiment. If the resolution was less than that, if it was 0.1 volts, for example, a lot of these readings would be the same. Okay. Right. What's next? Why did student 2 get different results? Okay, so apparently both of these students did everything correctly in the experiment, and yet student 2 got different results. How is this possible? Well, look at the numbers. 0.08, 0.09, 15, 20, 25, 31. Student 2 is getting smaller numbers than student 1. So he must be moving the coil slower. See, that's one thing that you can't control between the two students. You can't get them to move the coil at exactly the same speed. So even though they're both doing it correctly, they must be moving it at different speeds. Student 2 is moving it slower because he's getting smaller potential differences. Student 1's moving it faster. Okay. How do the results show that the investigation is reproducible? Well, if student 2 hadn't done this experiment and only student 1 had done it, then student 2 comes along and gets these set of results. He's shown that this experiment is reproducible because for both of them, they've both found that as they increase the number of turns, the potential difference increases. In other words, they've both shown the same pattern. So write that in your answer. Both set of results show the same pattern, suggesting that it's reproducible. Okay, state the process that enables a potential difference to be produced. Okay, so when you move this coil down past the magnet, a potential difference is reproduced. The process that I described is called electromagnetic induction. Okay, just use that exact phrase. Electromagnetic induction. Not magnetic induction, not electrical induction. Get it exactly like that, electromagnetic induction. That is the process by which you induce induction, a potential difference and therefore current in this coil, by moving the coil, cutting the magnetic field lines, and therefore achieving a changing magnetic field in the coil. That induces, a changing magnetic field in the coil induces a potential difference in the coil and therefore current. It's called electromagnetic induction. Right. State one advantage of a transformer that can be used with many different devices. They always put one stupid question in these. Okay. So we've got to think up an advantage of a transformer that can be used with many different devices. Well, it's more convenient. It's more economical. It's cheaper. Either of those will get you the marks. 1 mark. Stupid question. Okay, I think that's it. Yeah, there we go.